Hello and welcome everyone to our 6th tutorial video. So today we are going to do two things. First of all, we will try to gather some information that we have calculated in our previous video related to bands, DOS and dielectric. So we'll try to extract those information for future reference. Also we'll try to use two Python package uploads. So what that means is like when I initially was talking to you guys and I said that these are two files, mp-tools and mp-register, that we need to use, because if we don't use it as I will show you in that way, you will find some error during your investigation with PyDefect. So let's get started with that. So first of all, if you have been following my videos, so I told you that to follow this step-by-step guideline, and we have been following it throughout this video tutorial, and we are we have completed first 6 steps. So we'll start with this 7th step, that is the gather unit cell calculation result for future reference. So I'm assuming that you are in your, like, if I start that, yeah, so I will assume that you are in your, like, in the gallium unit cell folder, as we mentioned before. So first of all, what you need to do, you will need to come to the gallium nitride, this folder, and to do that you can just cd it, like it's mentioned here. You can cd to your root file and do this all other things. So sorry, not gallium nitride folder, you were supposed to be in the structure out folder. Okay, so let's be clear about that. So you need to be working in the structure out folder previously, before at the end of the tutorial number 5. Okay, so let's start with from that point onward, and now we are ready to, like, copy paste the course again. So let's copy this and see what it gives us. So first of all, we cd to the unit cell, because in the unit cell folder we have all these other folders. Okay, so very well. So let's see what it is working on. So initially we have, like, only these folders, nothing else. So what we'll be trying to do is, like, we need to extract all these different data that was observed in band, dielectric and DOS folders, and this is the code that is actually trying to parse everything. So let's give it a few seconds to complete. Very well. So it's completed now. Like, if we want to see the unit cell information, if I just refresh it here, you will see that unitcell.yml file, this file is created, and to print this file using PyDefect, the command is this. So as you can see here, some information like what is my valence band, maximum, conduction band, minimum. So if you just minus these two, you will get your band gap, and also electric dielectric constants values are also provided, and ion dielectric constants. So these are from, like, the from dielectric constant calculation. So yeah, we have all this information. Now what we need to do is this. Now this is very important, very important. Let me tell you that at this point you must do that, and it is that you need to download this PyRestor and PyTool from my GitHub rep. So let's download these two things. So first of all, I need to download mp-tools. Okay, I'm just saving it to my desktop, and also mp-register.py, and download it to this. So you need to upload it. So for the, like, mp tools, you just need to update one line, I think, and for the mp-register you need to upload the whole file. So to do that, you can just follow this, like, the command. So what I'll do is I will just run this whole thing. So as you can see where we are going, this storage home mvm7218, this is like my root folder. Okay, so if I just show you this, if I go to my home directory, this is where I am, like storage home mbm7218. So you need to find your own home directory, and you need to go to local library python 3 site packages. So after you are here, then in your home directory you just need to go to .local, and then bin local, I think, then library, then python 3.8, then site packages. So here you can also do it manually, or if you want to, you can do it by the code. So you need to go to mp api client mp register. So let me just do it manually for few minutes. So I need to go to mp register. mp api, sorry. Yeah, so mp api, then client, then mp register.py. So this is the file that I need to replace. Okay, so if your file is already there, you can do two things. First of all, you can just go to edit and just replace this whole things with the downloaded one. Otherwise, you can do is just you can delete this one and upload the one that I have shown. Okay, so that could also work either way. This is one part that you need to upload it, and that will work. And the second thing that also I must mention that this is the most updated GitHub repository. So this is not mine, but this is the main GitHub materials project API. So this is the file that is actually used for integrating your materials project key with the VASP or and PyDefect. So if you actually download my one from the GitHub and it still doesn't work, just come to this repository and download it, because every time it will be the most updated one. Okay, so here is the thing, that after you have uploaded your mp register, or you have copy pasted mp register from this directory, not this one, from this directory. So either case, you can just download these whole things, or you can copy paste these whole things, and you update this file that is under python 3.8 site package mp api and client. After coming here, you need to update one thing, that is that here, as you can see, the default materials API key, if you see that this is blank, it could be like this kind of blank, or there could be anything else. You make sure that you use here your own API materials project API key. So for my case, this is my materials project API key, so I am just using this one. So line 72 here, it's very important that default API key, you set your own materials project API key. Okay, so make sure you do that. Okay, so this is the first thing. And the second thing that we need to do is that you download this mp tools, that is the second one, this mptools.py, and replace it with the one that you have in your directory. So to do that, you need to, if I just come here, so this is the directory that you need to go. So let me just show you. So you need to go to site package, PyDefect and util. So to do that, let's go site package, then I need to go to the PyDefect. So this is PyDefect, and then util, and then I will have my this folder file mptools.py. So if you don't have it, then just upload it. If you have previous one, you can just replace it, or you can just delete it and upload the one that I have in my GitHub repository. Okay, so this is these are the two files that you need to update here. So after you have done both, then we are ready to get we are ready to go to that next stage, that is step 8. So step 8 is like creating completing phases and run VASP calculation of the completing phases. So what this step actually does is that when you are considering crystal structure of different types of atoms, like gallium nitride has gallium and nitrogen atoms, so it tries to do like what are the different types of combination in which these atoms can actually be present. So if I have gallium and nitrogen, there could be 3 scenarios. There could be only gallium, only nitrogen, or gallium nitride, right? But if I have like aluminum gallium nitride, there could be much more combination. Like there could be aluminum gallium nitrogen separately, or could be aluminum nitride, could be gallium nitride, or could be all together aluminum gallium nitrides. So these are the things that actually need to be calculated, and this is called the competing phases. So that we need to learn, we need to like perform calculation on. So let's start with that. So wherever you are in your present terminal, you just need to copy this. So here is the thing, like if you are considering only interstitial or vacancy defect, for vacancy point defect, you don't need to consider this file, because this file considers magnesium and silicon impurities, like the donor and acceptor atoms. But if you are considering only if you are also considering how the foreign impurity affects your point defect behavior, then you need to use that one. So for my case, I will be using this one, because I will be considering both magnesium and silicon types impurities, and I will show you the calculation where there are vacancy, interstitials, antisides, and impurities. So till you don't have any impurities, you can use that one for antiside, vacancy, and interstitials, but for impurity one, you need to do this. So another thing is that we need to add some files separately for interstitials that we will be covering after that one. So let's run this code. So first of all, what I need to do, I need to come to this CPD folder. So let me just, I think it would be better if I make it a little bit separated for you to understand it properly. So maybe I just need this, okay, because you either way you need to run first this command. So we are in step 8. Yeah, so let's run this first and come to our CPD directory. Why it's not showing? Yeah, I actually forgot to add mbm 7218. Anyway, so you just come to your CPD directory. There's the main issue. Okay, and then what you need to do is that you need to either apply this line or that line, okay, based on whatever your preference is. I am doing with the one with magnesium and silicon impurities. So I have gallium and nitrogen in my basic cell structure, and I am using silicon and magnesium in addition to that. So just copy this and just paste it. And if I go to like the CPD folder, as you see here right this moment there is nothing, but after this calculation there will be a lot of files hopefully. So I am going to pause this video and I will run each of these, you know, like each of these these files till all are completed, and then I will return again in this calculation. So as you can see in each of these, like for the first one when I am considering gallium and nitrogen, let me just clarify something for you. So in this line you see gallium space nitrogen, so this means actually that gallium nitride, and here only gallium, and then there is nitrogen. You can also play with the above Hall energy, and there is like silicon and also silicon above Hall energy. So all the different combination that you want in your CPD program, you can just run it. Okay, so if you make sure that you run separate CPD program for each. So if you have aluminum gallium nitride, for example, you run for aluminum, for gallium, for nitrogen separately 3 programs, then aluminum nitride 1 program. So there's 4, then gallium nitride another one, this is 5th, then aluminum gallium nitride there's another one, this is 6th. So total 6 files. Okay, so try to finish everything that way. Okay, so as you can see, all of our files have been created. If I just come in CPD folder and refresh it, you can see that all the different combination has been created. Now if I go into each of these, you can see that there is like a postcard file and prior info.yml file. So if you want to read this YML file, just go to this terminal and write PyDefect.print, then this. So if I just show you quickly, so all you need to do is go to this folder and write PyDefect underscore print, then this. Then you will get some information regarding like what are the previous data so these are the data that the program itself actually extracted using your materials project API. So it searched our materials project API and learned attached some background information about that materials, like the total magnetization, band gap, etc. Okay, so very well. So we have done this part. Now we need to create VASP files, because as you can see here, I only have the postcard of each, right? I have only the postcard. So as you know that when we are using PyDefect, if we have only postcard, I can create all these files in a automated fashion using the VASP commands. So similarly, I will be using like basic for loops to that will move to each of these folder, and then we'll try to create the required VASP input file. So as you can see here, in each of this folder there is like only postcard. Okay, so let me just clear this a little bit and run this command. So as you can see, I am telling it to go to each of this directory. So it will go each of these 5 directory and will create the we create the VASP input files using VASP and return. So let's wait for that and let's see after it is finished. Okay, so the program is actually completed. So if I go to each of these folders now, as you can see that each of these has the record files. Now as you can like, I think you have been following my previous videos also. So as you know that when I am trying to run VASP, I need the run.slurm or any .slurm file that I don't have here. So I need to make sure that I have the slurm file here, and then I will be able to run. So as you can see, if I just run this command here, what it will do, that it will go each of this directory like the before, each of these 5 directory, and then it will copy run.slurm file from one of my previous calculation, because it doesn't matter since this is a unit cell, I can use the band structures, the slurm from that I actually run during the band structure calculation. Okay, so that it will do, and then I am actually running as batch file. So during this for loop, what it will do, that it will go to each of this directory and it will copy slurm file from one of the other previous band structure calculation, and it will paste here in each of this folder, and after pasting it, it will run this whole folder. I mean the VASP calculation will be done for this whole folder, and it will go to the next one. Again we'll copy paste the slurm file here, and we'll run this whole calculation till all of these 5 folders calculation is done. So I am after running this, what will be the output, I'll show you. So let's go to this folder and see the outputs after all these outputs are calculated. Okay, so all these files have been actually I have calculated all this by VASP calculations. As you can see, for each folder the calculation is already completed. Now we'll do some other things. So after doing that, we will create the composition energy.yml file. This is important because it collects the calculated total energy, and also we can see the output file by using the PyDefect._print command. So let's copy this. I think I have a typo here. This should be file. Let me just correct it. Okay, so I have corrected it, and I hope now it's ready. to just copy paste this thing. Yeah, so just copy this thing and it will automatically purge every data that this CPD folder actually has, and then it will create the composition energy.yml file. To print it, you can always use PyDefect_print. So as you can see here, you can see all these energy levels. Let's come to this here, and we can also create some relative energy.yml and standard energy.yml file. And to do that, just we need to just copy paste this thing here. So always remember which directory I'm working on and try to do it from there. And if you have been following the directory tree properly, there shouldn't be any issues. So these are all the files that have been created. So if I just refresh it, you will see that all these files are actually here. Also, you have the convex Hall diagram. So this convex Hall diagram was created in our Lux, just this command. So if I want to show you like how it is, so this is the convex energy diagram using all these different types of atoms. Gallium, you have silicon, magnesium and nitrogen, and all the diagrams. Also, we can create the CPD diagram, that is the complementary phase diagram, and chemical for diagram.json file. To do that, we just need to copy this section and just paste it here once again from the CPD directory. And okay, so if I just refresh it here again, you will see that there's some more files have been created. So there is like the chemical potential diagram and also target vertices.yml file, and finally okay, and finally we have this in this code we have the last line PyDefect PC. Running this, it will create the chemical complementary phase diagram, CPD diagram. So just run it. And after running it, you will see that there will be another plot, that is cpd.pdf. So this is a very important plot. So what that means is like when you have this structure of gallium nitride, one side you have very high so one side you have very high nitrogen rich environment and another side is gallium rich environment. So I am requesting you to focus on this two part that is pointed out as A and B. So if you have been reading the literature, you would know that when we are calculating formation energy diagram, there is three scenarios that we can do it. Like for gallium nitride, we can do it in a normal condition, like for gallium nitrate, that's it. And there is nothing about richness, whether it's gallium rich or nitrogen rich, doesn't matter. But in some cases we want to see how the gallium rich conditions formation diagram looks like, and also in some cases what the nitrogen rich formation energy diagram looks like. So in that case, we need to make sure that we are using A as a notation, that means the gallium rich, and B as the notation for nitrogen rich. Okay, so also you can see that the chemical potential gallium and nitrogen at gallium rich condition is like -0.9 and nitrogen rich is something above 0. So you can also compare this to validate your result. I will suggest that you read this point defect calculation, gallium nitride point defect presentation file, and at the end of the file you will find some information like how to read this CPD diagram. Okay, so with this we are at the end of our CPD diagram formation. So we have created all these things, CPD, convex Hall, and all those things that you could use for further calculation. So after that, we will start with adding the defect to our structure. So till this CPD point, we have only considered unit cell. So after this very point, we will try to create a supercell, and we will try to add different types of defects in that supercell. Okay, so in our next video, since it is becoming a longer one, we'll try to work with the supercell and defects. So I'll see you in the next one.